CS1010X Lecture 8, Working with Sequences. Lecture 6 and Lecture 7 are on functional abstraction and data abstraction. Both of these are to help us in managing complexities. In this lecture, we see working with sequence, in particular tuple again, and we will examine the use of tuple in the recursion and iteration algorithm. We will take a look at signal processing view of a computation so that we can sequence out the processing to also help us manage complexity. And then we will look at processing of tree, which is an important data structure in computer science. And tree, as will be presented here, it's a tuple of tuples. In the previous cases, we deal with linear kind of data. Here, tuple of tuples, it's a kind of non-linear data structures. Before we work with sequence, let's take a look at what is a sequence. Sequence versus collections. Sequence has the notion that items in the group has certain order, meaning that it comes one after another. So you have seen tuple as a sequence, and this is immutable sequence. It is represented with parentheses. We will see list as a mutable type of sequence in lecture 9, and it is represented with a square bracket. String is also a special kind of sequence with its characters coming one after another. It is immutable and it is represented with a code. Now, what is a collection? Collection is ordered or unordered group of items, whereas sequence is ordered set. Collection can be both ordered set or unordered set. Tuple, as we know, is a sequence. It is also a collection. Members in the tuple can be duplicated, meaning that we can have the same member appearing more than once in the tuple. And list is also a collection, even though it has order. And it allows also duplicated members. Dictionary, as you will see in subsequent lecture, it is actually unordered, mutable, meaning that it can be changed. It is indexed, meaning that it has certain feature to help in retrieving the data, but it doesn't allow duplication. Set, as you understand it from high school, a collection of items, and it is unordered, it is mutable, it is unindexed, and no duplication is allowed. And this set is represented with curly brace, whereas the dictionary is curly brace with a colon because there is the item, which is the key, with its corresponding content. The key is the one that doesn't allow duplication. All these tuple, list, dictionary, set, strings are primitive data types. Python system provides lots of support to these primitive data types, such as tuple here, with the so-called methods, which are actually functions. Once again, for our learning, we do not need to know all of them. You just need to pay attention to remember those methods that we cover in lectures, tutorials, or recitations. If there's any need to use all these in our formal assessment, we will provide them in the assessment paper. So here is the link that you can go to, and here's the list for the list method, dictionary methods, set methods. We can now continue our learning on working with tuple. Here are the basic operation we know working with tuple. How do we get the first element of the tuple? We simply have tuple square bracket 0. This is the first element of the tuple. Now, the time to do this, it's constant. You simply take out that element at that specific position. And of course, the space is constant too. The space can never be larger than the time complexity. Get the rest of the elements excluding the first. We know we can have the tuple starting from 1 until the end. And what is the time in this case? Because tuple is immutable, so when you do this, you are actually creating a new tuple, and the time needed is 1 less than the number of elements in there. So this is the time, it's O of n, where n is the number of items in the tuple. And the space, because we are creating a new guy, so the space we need is also 1 less than n, so this is also O of n. You get the last element of the tuple, you simply just refer to the last one, minus 1, and of course the time it's constant and the space is also constant. What about getting the rest excluding the last? It is like this, starting from the beginning until before the last, so you don't have the last guy, and the time is also O of n because tuple is immutable. So this operation is to make a copy of the tuple excluding the last guy. The time is n minus 1, which is O of n. And the space is also the same because we needed to create a new tuple with elements excluding the last one. All these operations are ideal to support recursive algorithm with tuple. The key idea of recursion is to handle the first element and then the rest, or you handle the last element and then the rest. The rest here refer to the second until the last. So this recurs up the sequence. The rest here means that the first until before the last. So this is recurs down the sequence. Here is our first example, reversing a sequence or a tuple. For a given tuple, we want the reverse of the tuple. For example, 1, 2, 3, 4 as the input, we want to output 4, 3, 2, 1. So the code looks like this. Define, reverse the sequence. If the sequence is empty, you return empty. This is the base case needed for recursion. Otherwise, you return the reverse of the sequence starting from the second item until the end, plus the first item. Alright, so now the first item appears at the last. The rest of the reverse sequence appear in the front. So this is the definition of reverse. Now, but if you run this, it will cause an error because this is a tuple, this is an element. So a tuple cannot be concatenated with an element. You need to make this element into a tuple of one single element. Then you can properly concatenate a tuple with a tuple. So this is a solution. So note that tuple has to be concatenated with tuple, so this has to be made as a tuple. Secondly, the time is O of n squared y. As you see, you have this recursion that has to go from n items in the tuple to get n minus 1 items in the tuple and then n minus 2 element in the tuple, and each time you need n minus 1 effort, n minus 2 effort, all the way until 1. So the sum of this AP is n squared as you learned in high school. Same for the space. You need to create a tuple of n minus 1 items, then tuple of n minus 2 items upon entering into the recursion until a tuple of 1 item. So it is the sum of n minus 1, n minus 2 until 1. Again, this is n squared. If you go to Python tutor, you will see this for yourself. This is the same code. If you try to reverse 1, 2, 3, 4, 5, you will see that the reverse it's called, and then you have a sequence which is 1, 2, 3, 4, 5. You needed to create a sequence of 2, 3, 4, 5, leaving out the first item. Then you need to create the sequence of 3, 4, 5, leaving out the item 2, and so on, until the end, empty. And then you backtrack to get your answer. So this shows that the effort here is already n minus 1 plus n minus 2 plus n minus 3, and so on. So therefore, you have n squared as the time. Also, the space is repeated here. You need n minus 1 space, n minus 2 space, and so on. So the space is also n squared. We saw how to do from front to the back. So this is the second version of reversing a sequence from back to the front. So the base case is when it is empty, it's empty. Otherwise, you return the very last guy plus the reverse of the remaining guy from the first till before the last guy. Of course, here again, you should not forget that this single element should be made into a tuple to be concatenated with tuple. And the time remains the same. It's also from the sum of n minus 1, n minus 2, and so on. And the space is of the same reasoning. For this version, this is what you see in Python tutor. To reverse 1, 2, 3, 4, 5, you will have 5 strip off, 4 strip off, 3 strip off, 2 strip off, 1 strip off, and you get empty tuples. Then you reverse back to get your answer. For this same problem on reversing a sequence, we can solve it in an iterative manner. We can handle the first element and then the rest. For this, we mean that we move forward the sequence one by one. Or we can first handle the last element and then the rest. For this, we mean we move backward one by one in the sequence. Here's the code for reversing the sequence in an iterative manner, our version 3. So define, reverse the sequence. First, you initialize the result to be empty, and then you take items in the sequence one by one, and each time you take an item, you append it to the result, and then you return the result. This shorthand means that result equal to result plus the tuple containing the item. But this is in the wrong order, so this is incorrect. We should put the item in the front of the result. This is a similar code to this, except that the result now is equal to the item that you just took out must be put in front of all the last result so that this actually achieves the reversal. The above is just to remind us to be careful with concatenation to respect the order that you want. The time is still n squared because you have to create the result with one item, result with two items, and result with three items until n items. So the sum of this is n squared. On the other hand, the space is just O of n because the result can reuse the space. That is to say that when the result grows from one item to two items and so on, the old version of result with I minus 1 items need not be kept when you already have I items. Thus, the usage of the space does not accumulate to On squared, but at On only. This is how it looks like in Python tutor, reverse 1, 2, 3, 4, 5. When you run it, you will see that the result, the longest that you need, it's just the length of the tuple. And so the space is O of n. But because tuple is immutable, so result is of length 1, length 2, length 3, and so on. So the total sum of the time you spend to create the result is actually O of n squared. Here's the other version of the reverse iteratively from the back to the front. So initialize the result to be empty, and then you take item from the back one by one until the end. Each time you take the item, you add it to the result. Again, this is just an illustration to tell you that the order is wrong here. It has to be this, which is result equal to result plus the item, rather than item plus the result. You can see that this actually gives you back the original sequence with no change. This is the one that gives you the answer with the sequence reverse. At the time is On squared. Again, this is a sum of 1, 2 until n because the result has one item, two items until n items. You need to spend time to create them, and this sum up to be n squared. As for space, space is O of n, just like the previous version. You can reuse. At this point, you should feel that we have certain pattern in our program to deal with sequence. This is indeed what we did in lecture 6 to then extract out higher order function. We can also do it for sequence, as you see in the following slides. Here is an abstraction as accumulate. The reverse function is base case and the recursive part. So for accumulate, it is accumulating based on the functions with the initial value and input sequence. If the input sequence is empty, you will return the initial value, just like the input is empty sequence, output is empty sequence. Otherwise, you return the function that you pass in to act on the first item with the result of the rest of the items. You can figure it out that the time and space is as what we discussed previously. Similarly, you should be able to do accumulate for iterative version. Let's see how we can translate reverse into accumulate. With accumulate like this, our reverse is now like this. So define reverse sequence, return accumulate, the sequence is at the back, and the function to do the accumulation is x refer to this and y refer to this. So whatever reverse answer you already have in y, concatenated with the single item put into the tuple. And at the end of the sequence is empty, you return an empty sequence also. So this is reverse in terms of accumulate. Actually, it's natural to see that accumulate can do summing up of all the values inside a sequence. So accumulate lambda xy is equal to x plus y. This is the function to do the accumulation with the initial result to be 0 and the input sequence here. And the time and space, as you can figure it out, they should be the same as before. Accumulate is an example of processing sequence by going through each and every element. For here, accumulate is a sort of summarizing the elements up. In the following, we will see a few more useful functions to go through each and every element in a sequence to do something. These are the mapping and filtering. Mapping is to perform an operation on each and every element of a sequence. Like here, A, B, C, D are the elements in the sequence. We want to apply a function f to each and every element to get FA, FB, FC, and FD. Here it's the recursive thinking to achieve this. If the sequence is empty, then you return empty. Otherwise, you return the function applying on the first element concatenated with the function applying to the rest of the sequence in the recursive manner. So the time is O of n squared and the space is O of n squared because sequence has to be constructed of size n minus 1, n minus 2 until 1. And since the space is O of n squared, the constructions actually also implies that the time is also n squared. In the iterative manner, you can also do the same thing. by going through each and every single element one by one, and each time apply the function on it and then concatenate to the rest of the result you have so far. And of course this is then O of n squared for the time still because of the construction of all these subsequences. But the space can be reused as before, and therefore it's O of n only. Here are two examples. Map is like this. So to square each element of a sequence, that is, the function will be the squaring of the elements. So you simply say define sequence square, input sequence, return the mapping. Function is upon input x, it produces x squared, and the input is sequence. To double each element of a sequence, there's not much difference except that the function now is, instead of x times x, is x plus x. About the time and space, you can figure it out. This should be obvious. The next is a filter. We see that mapping is to do something to each element. Filtering is to filter away things that we do not want, or keeping whatever we wanted. Again, the recursive thinking following this same trend of thought is simply this. If the sequence is empty, there's nothing to keep. Otherwise, the input predicate, this is the conditions that to check whether it fulfills. If it fulfills, you keep it and concatenate with the results of the processing of the rest of the elements. Otherwise, for that element that you have that fails the condition, you simply skip it and continue your processing with the rest of the elements. The time and space is n squared still, as this is obvious. Iterative version, you can do it too. And the time and space is respectively n squared and n. Here are the examples of using filter. Suppose we are to keep numbers that are even in a sequence, then the predicate will be the lambda to check that if it is even, then you return true, otherwise false. So sequence even is simply return filter lambda x. If the remainder of x divided by 2 is 0, then it is true, otherwise it is false. So equal to 0 is even numbers. So this is the correct predicate that you needed. To keep only number divisible by d, define sequence divisible the sequence d. The function is then with the input the sequence number x. If x divisible by d means that is equal to 0, and that's it for the function. Once again, times and space are obvious. To work with sequence, we must have the sequence in the first place. As you saw in lecture 7, we could read out the sequence from afar. For here, we show a way to enumerate a sequence for our examples. Define enumerate interval low to high. We want to generate sequence from this number to this number. So you just return the range from low to high plus 1, because the range does not include the last guy, and make this into a tuple for our use. So for example, to generate 5 to 20, you simply put enumerate underscore interval 5 for the low, 20 for the high, to get you 5, 6, 7 until 20. To generate even numbers from 5 to 20, so whatever you generated here, you want to filter out to get only even numbers. So you can do filter, so lambda x with this function to test for even number, and for each of the number generated by this enumerate underscore interval. Or you can write sequence underscore even, which is the filter function on this particular range of numbers. Now, this is also an example to show that we can combine the various tools we have acquired till now to solve a more complex problem. Indeed, we can easily combine these tools of accumulate, map, filter in some way to solve complex computational problems. This is the perspective of computation in a signal processing manner, as we discuss next. Take the example of the music signal. It is produced by a player, which is the producer. It feeds into the amplifier and then sent to the speaker to convert it into sound for consumption by the listener. So the music signal goes through various stages of processing before it reaches the consumer. In all these stages, we can have additional components to be inserted, like the case of the music produced by the player could be fed into a filter before it enters into the amplifier. It is easy to change component, like the case here that the player is now replaced by the radio. So the signal is the one that interfaces among all the components. When you relate this to our computation, you can see that we also have producer, which is our enumerator that creates the sequence. We had this enumerate underscore interval, the low to the high, and we also have the filter that removes some elements in the sequence, And we have a mapper, which modifies the signals with a function. And we have the consumer, which is the accumulator that consumes the signal by aggregating or by summarizing the sequence. And all this plus what you're going to learn in lecture 9, sorting and searching, these are pretty much the kind of computation that we have to deal with in most applications. Now the benefit is that you see modularization, and each component is independent of others. A component can be replaced and be reused. And it is clear, it separates the data, which is the signal, from the processing, and it is flexible as new component can be added. Let's take a look at some examples. For this one, sum of square of odd integers. We had this in lecture 6. We used this higher order function with the term, which is the function applying to it, and from A until B, and how to get from A to B is through the next function. So to get sum of square of odd integers from A to B, we simply call this higher order function sum to apply the term as x squared here, and from A to B, we increment it each time by 2 to get from one odd number to the next odd number. This is how it was in lecture 6. Now, in signal processing view, we enumerate all the numbers from A to B, and we remove those that are non-odd, and we do a square to each of the number, and then we accumulate it. So this is a pipeline that it solves the same problem. Here is the code. So we have enumerate underscore interval from A to B to get all the numbers between A and B. And this sequence is passed to the filter to check whether a number is divisible by 2. If it is not, then this is equal to 1. The number will be kept as it is an odd number. If it is divisible by 2, then this number will be discarded. And then for the number that we kept, we apply the square to it. And then this map created a sequence that will be used by the accumulate to sum them up. So this is a 4 stages solutions from the signal processing view. Here is another example. We want the sum of even Fibonacci numbers. That means Fibonacci from 1 to n, we only want those that are even to be summed up. So here is the signal processing view of how to do this. First, we enumerate from 1 to n all these integers. We find their Fibonacci values. Then for those values that are even, we keep them and we accumulate them as the answer for output. Here's a Fibonacci function that you're familiar with. The solution is as what we discussed just now in the pipeline. So define sum of even Fibonacci numbers. First, enumerate from 1 to n, and this sequence is passed to mapping to map each number to its Fibonacci number. Then all these Fibonacci numbers are fed into filter to check if it is even, then be kept for accumulation as the answer for output. Just a quick note to say that our PE questions in the past on file processing can often be solved cleanly with signal processing view too. Here is an important note that you should keep in mind. We often have this recurring theme in courses in higher education. That is, there are already features, functions provided, in this case Python, that has map, filter, and accumulate. Yet you saw over the lectures that we built map, filter, and accumulate ourselves. Why is that so? One reason is that Python has it, but it doesn't mean other languages have it too. We need to know how to build it ourselves in the event that you work with other languages. Usually we build a simple version to illustrate the purpose. Python's versions of map, filter, and accumulate are actually more powerful. As you can realize, this is not a course about Python per se, and so you don't have to know Python reference menu well. In all our assessment, should there be a need for referring to Python reference menu, we would have provided it to you in the assessment paper itself. Having said all this, let's see Python's version in the next few slides to get a better feel about Python. Python's map, filter, accumulate, they output iterators rather than explicit tuples. They work for sequence in general and not just tuple. We will explain iterators in the following. Here we have A equal to map lambda x plus 1 on this particular list. The output A is a map object. When you try to print the items in A, you will get 2 because 1 is mapped to 2, 2 is mapped to 3, so you get 3, 4, 5. When you try to print it again, you get nothing. Why? Because this is an iterator. iterator has content, and once you use up the content, it is empty. Now if you take our map in our earlier lecture notes, you see that it doesn't work for list, whereas the Python map does work for list because we have explicitly put down a subsequent which is assumed to be a tuple. Here's an example of filter in Python. B equal to filter lambda x. When the remainder of x divided by 2 is equal to 0, that means that we are interested in only the even number, working on the list 1, 2, 3, 4. So the output B is a filter object. If you try to print out the content of B, you get 2 and 4. When you print it again, you get nothing because this is an iterator, as we say. Once you have used the content, it is gone. While B still remains a filter object, there's actually nothing in there. Here are more examples about iterators. An iterator is an object that contains a countable number of values. It can be iterated upon with the method iter and next. Iter is needed to convert an object to an iterator. We don't see in our example here. In using next to iterate over an iterator, once a value is used, it is gone. To be able to use an iterator over and over again, you can convert it to a tuple or a list before using it. Here's an example. We have a sequence which is 1, 2, a tuple 1, 2. We map this sequence to its square, so we have a sequence iterate, and sequence iterate is a map object. When you say next sequence iterate, you get 1, which is the 1 square. When you next again, sequence iterate, you get 2 square, which is 4. When you next once again, there's nothing else in there, so you get an error. Let's do this again. Sequence equal to 1, 2, the tuple 1, 2. If you have this sequence iterate from the map of the tuple to its square, you print it once, you get it. You print it second time, you get nothing. Here's another example. Sequence equal to 1, 2. Sequence iterate is as before. If you put sequence tuple equal to tuple sequence iterate, so sequence iterate was a map object, but it has been converted to tuple to become sequence tuple. So when you print sequence iterate, there's nothing in there, because you have taken out all elements in sequence iterate to make them as elements in sequence tuple. But if you print sequence tuple, it has it 1, 4. You print it again, it's still there, 1, 4. So this is how you can keep the answer from map to be used over and over again. We now see working example with Python accumulate. If you say accumulate the function, this is undefined. You need to import from iterative tools to then use it. So we have accumulate the sequence and the function to apply on the sequence to get C. So this function is to add two items together. In effect, it takes any item and add all items before him into itself. So when you print it out, you see that C is actually 1, 3, 6, 10, because 1 is from 1, 3 is from 1 plus 2 to get 3, 6 is from 1 plus 2 plus 3 to get 6, 10 is from 1 plus 2 plus 3 plus 4 to get 10. Once you have printed it, if you try to print it again, you get nothing as before, because iterate objects, it's consumed once it is printed out. As you see, when you print it, you get nothing. Here's another example on accumulate. Given a sequence x1, x2, x3, you want to output a sequence y1, y2, y3 where yi is the products of x1, x2 until xi. Previously, in the last example we saw was yi is the sum of x1, x2, xi. So you have accumulate 1, 2, 3, 4, 5. If you take the function lambda xy, x times y, and accumulate it, you will get d. D is then iterate tools dot accumulate object. If you print it out, you see 1 as the product of itself, 2 is the product of 1 times 2, 6 is the product of 1 times 2 times 3, 24 is the product of 1 times 2 times 3 times 4, and likewise 120 is the products of 1, 2, 3, 4, 5. If you try to print it out once more, you get nothing. D is an iterator. You print it, you get nothing because it has been consumed here. You can check our own accumulate function to see that we output only one final answer. And in saying so, actually our version is the same as Python's reduce function, that you can look it up. In our work and assessment, should there be a need to differentiate between our own version of map filter on accumulate versus the version of Python's, we will make clear in due course. That's all for this video.